Okay, I'm going to go through chapter one's lecture slides, general principles. Okay, so what we're going to do is I'm going to talk about give an overview of mechanics and kind of where statics sits in there in that structure. Then we're going to look at the SI System International and the USCS unit systems. I'll take a quick look at some unit conversions and also cover Newton's laws. Okay. Engineering, what it is, basic idea. You'll see, definitions are all kind of similar, but may not be worded exactly the same. But basically, what you're trying to do is, use science and math to actually solve like a real world problem. Okay, and this is engineering statics, so it's the problems that we're going to be looking at are physical problems or physical structures. Okay, but it's used in all sorts of areas. Um, So, what do engineers use? Of course, previous designs. So they learn from past things that things that happened in the past, designs that happened in the past, um, any kind of experiments, some creativity, some new designs potentially, and then mathematical models. And this is kind of where we're going to be in this class. Is that we're going to go through and analyze different physical systems. Okay, in terms of from the perspectives of a static behavior. And statics really is basically what we're saying is there's two sort of main points. We're going to get to the point where we do an analysis where we want, such to say, a structure not to move or have very little movement. And the second one, of course, our analysis could be something that's moving but has like constant velocity and um, you know, maybe fixed altitude, let's say, constant velocity and fixed altitude, which is also a statics problem. Okay, so the two main points is that all the forces, so if you took and you made vectors, direction plus magnitude, added all the forces of a system together, you would come up with a total that's zero, which essentially means there's no acceleration in one direction or another. Okay. The second part of this is that there's no rotation. So if you had vectors that represented rotation with a direction, so it has direction and magnitude on a system, that all of those would sum to zero. Okay, so those are kind of our two main points or uh, main concepts that we're going to be working toward on the class. And initially, we're going to start talking about some of the things you've probably already seen in Intro to Engineering, where you're trying to find like a resultant force or resultant rotation or what they call a moment or torque. Okay, so we'll start with that. Um, Interesting video to watch, so you can go and watch this video. If the link, I think the link still works. Um, but it's more for your amusement than anything else. Okay. So engineering and practice, different types of engineering fields or disciplines, and this gives you kind of the idea of what each of them does, right? So here's an example: passive space shuttle can follow, or actually could be any kind of aircraft, right? Civil engineers, physical structures that don't typically move or not designed to move or maybe designed to move a little bit. But basically these are, systems in equilibrium. And then mechanical engineers also. So this one's more concerned with the mechanics of a device or motion potentially. So the things we're going to look at really pretty much fall, you know, under here for the most part. Okay. Branches of mechanics. So what we're talking about is this idea of rigid bodies, all right? And that's really what we're going to be dealing with. So we have statics, and here's where dynamics falls into. This one, what's the difference really? Acceleration. In dynamics, you have acceleration. In statics, you don't, okay? And that's really where it falls in. And the only thing when they talk about rigid bodies is they're basically saying it's not changing shape, or it's so small we pretty much ignore that change of shape, right? So here's mechanics, what it is. So this basically just talks about, the previous diagram, right? So you have rigid body mechanics. So we're rigid body mechanics, statics, and dynamics is also falls under rigid body mechanics. All right, statics and dynamics, and like I said, statics deals with equilibrium, and what I said, all the rotations sum to zero, all of the forces with directions, the vectors sum to zero. Okay, so there's the real difference between the two. Equilibrium. So this is what I'm talking about. Uh, you could say this is really kind of what we're getting to. Of course, some of our original problems we'll be looking at, it may not be in equilibrium. Okay, but basically it says all the torques or any rotations are going to be zero, and all the forces acting on it zero. So it might be that part of the analysis is you have to determine if it is in equilibrium. Well, in engineering statics, typically we want it to be in equilibrium, so you might have to determine, hey, is this system in equilibrium? Okay, all right. So, but at first we're going to be looking at forces, force vectors, and then shortly after that we'll start looking at torques also. Okay. Oh, here's some. I had some nice photos here of different structures. Here's bridge. Interesting bridge. Uses like trusses, right? Truss structure here. Thin members with triangles, which we're going to look at trusses. It has the shape, right? So we have like an arch shape also. And it looks like here there's cables. So it's a suspension bridge. So it has all those characteristics in it. Okay. Here's another building, right? And so what we're concerned with is, designing it, making sure, of course, that it can support the weight in addition to, any other things that might happen, be somewhat earthquake proof or wind proof, strong wind is not going to take this down. Aircraft, all right, if this thing's flying at a constant altitude, constant velocity, it's actually a statics problem, right? Okay. Okay. So we'll go through Newton's laws briefly here. Okay. So basic idea, first one, every object in a state of uniform motion stays in that state of motion unless something else acts on it, okay? So our assumption here is that if it's moving off in this direction, what it really says is that the x component, if you were thinking about this as two components like a y, this is, what you had covered in Intro to Engineering. You have a y component. If we made a coordinate system, let's say vertically is y, and horizontally is x, what we're saying here is that whatever component acting in this direction from F1 is greater than the component of F2 acting in the opposite direction, right? Along the x. So we'll get that velocity. And the other part of it is that whatever y components of these two must equal this one, right? F3. Okay? And that would give us velocity off in this direction. All right? But you recognize that if you had some forces acting, and of course it could be an equilibrium condition, or it could be it's a velocity acting off in a certain direction. But the basic idea is this: whatever motion it has, there has to be something, a force acting against it, in order for it to stop motion. If you took your car and rolled it down a hill, eventually it would stop, right? It's not going to keep going off into a certain direction. So what's working against it? Well, you have, wind resistance, and initially it'll go down as it gets slower, but and you also have friction, right? Rolling friction and friction of the tires on the road and some, the axles inside the bearings. Those things together would eventually cause it to stop, right? Okay. The second one is that what's the relationship, right? You have some force acting on an object, and whatever its mass is times its whatever its mass is. So if it's force divided by mass, you can actually figure out what the acceleration is, right? Or if you knew its mass and you knew its acceleration, you could figure out the resultant force. Okay. Now, you could represent this as like this is a resultant force. So this could be all the forces added together. You come up with one force that represents a force off in this direction. Okay, but this is just telling you what the relationship is between them, right? Okay, and the third one, every action is equal and opposite reaction. So these two strike. If we're going to look at objects like this where you have two, if this one's pushing off in this direction with a certain force, the other one's going to be pushing back with that force. Push my hand against a wall pushes back with the same force. Okay. All right, units of measure. There's basically 7 fundamental quantities in physics. We only care about these 4. Okay, so these are so-called, these are fundamental physical quantities or dimensions, fundamental base dimensions. You might hear that term used also. Length, mass, time, and force. And what we're going to find is that any of the other units that we use, be it velocity, which is length divided by time, or acceleration, length divided by time squared, or second squared, or time squared, if you want to think about it that way. Everything else is a derived unit. Okay, so these are our 4 base units, everything else derived. Okay, so we have our 2 different unit systems. SI system, USCS system, used to be called like the English system, but not very many countries use this now. Maybe a small handful, 2 or 3, maybe 3 now. USCS system, okay, and basically, USCS system. This is what we use in the U.S., and this is pretty much everybody else in the world uses this, okay. And the key point here, of course, is that know what system you're working in, and don't mix and match different units in the different systems. If you have to make a conversion, you should basically make a conversion at some point, or make it at the end. After you go through all the calculations in one system, you make in the end you make the conversion. Okay. Here's the units. Okay. And the only thing is here is that Newton's actually derived unit in when you're talking about SI system, and this one is a slug is a derived unit when you're talking about the USCS system. Okay. Overall, these are, if you look across here, you'd see the 4 base units from that, but these are actually derived depending upon which unit system you use. Okay. Some conversion factors. Right. There's some common ones we're going to use in this class. Okay. So the one point to make is when you go through and work on problems, is that you don't change units. Don't change the unit system, or unless it asks you to change it. Right. If you're in USCS, give your answer in USCS. If you're in SI, give your answer in SI. Unless it's required as part of the problem. Okay. So you could go through the process here, right, and solve for this just by essentially multiplying it times this, right? Because when you're talking about like a conversion factor, what are you really saying? You're saying, I'm only converting, right? I'm multiplying it by a quantity 1. So the conversion factor for this problem would have been 4.448 newtons divided by pound, right? So then when you went and converted, you would cancel out pounds and be left with just newtons. Okay. Okay, here's the SI system. Some things to pay attention to when you're using it. Don't do plural, right? It's kilogram. Don't write 5 kgs, okay? You have units, you would separate them with a dot, okay? So like meters, seconds. Because if you didn't do that, this potentially could be milliseconds, right? So and they know that it's meter seconds because M is used both for milli and for meters. Okay, so this will avoid that confusion. Most are in lowercase, except there are a few that this pascals, newtons, mega, giga. These are everything else is in lowercase except for these. Okay, for anything we're going to work with, anyways. Exponential powers, of course, this centimeter is just centimeter squared. Okay, and don't use compound. Don't do mega, giga, or something like that, or milli, giga, or don't use compound prefixes. Okay. Here are the common prefixes that we'll use in this class. Okay. Pretty much, I think that may be everything we use here. Okay. One more, 2 pi radians equals 1 revolution, or, 1 revolution, 2 pi radians equals 360 degrees, let's say. Okay. Okay, gravitation. All right. We all know gravitation keeps us on the planet, otherwise we'd be floating around in space. Okay. And what we recognize, from not from experience, I wouldn't say, but is that maybe past observations that we've seen before and talk about it, is that like on the moon, of course, people weigh less. The mass of objects is the same, both Earth and Moon, except the gravitational attraction or acceleration is different. Okay. There's a form. Here's the general equation when you have two objects. Here's the force between the objects. Here's this universal gravitational concept, and you have the two masses, and then you have essentially the distance between the centers of these two objects is r. Okay, and you can figure out the force between them. When you're dealing with Earth, okay, there's one thing that we have to represent the acceleration, because this is just F equals ma, right? G is just the gravitational acceleration of the Earth. But this is how you'd represent it. So if you wanted to figure out, if you had something further off from the Earth, you could figure out what the gravitational acceleration is toward the Earth, or the gravitational acceleration. You use your equation to figure out the weight is. So if this is off of the surface somewhat, what would happen here is that this represents to the center of the Earth. This is fixed, essentially fixed. And this is the distance from the center of the object from the center of the Earth, right? Okay. So what you would observe here is that as this would be fixed, right? If you had an object, let's say a satellite or something off of the surface, the acceleration toward the Earth's surface, this number would increase. So the acceleration toward the Earth would decrease. And eventually you get far enough away, this just becomes negligible, right? Because this number keeps increasing as you get further from the center of the Earth, from the surface of the Earth, you could even think about that. But further from the center of the Earth, as you get further and further away, eventually this term just takes over and this term becomes zero, and there's essentially like no weight or no attraction toward the center. Okay. Well, if these two are the same, right, which means you're essentially on the surface of the Earth, right, then then A just becomes G, because that's all that's left in this equation. This just becomes 1. So then weight, of course, it's just going to be m times G. Okay. Numerical calculations. Just so that we follow some standards, we're going to do 3 significant figures. And they say use at least 4 for intermediate calculations. Well, if you're using a calculator, you can just leave the default, right? However many significant figures it uses. And then when we actually go, see textbook for explanation. Yeah, this one we can round it up. Be consistent with rounding off. Okay. All right. So greater than 5, we round up. So like here's an example of 3 significant figures, right? And so let's say your answer came out to be this. You would represent it like this, right? So if your calculator gave you this is how you would actually show it. And if it's smaller than 5, we're going to round down. So like this is 4 figures here, right? And we round it to be 3 significant figures. Why? Because we make this one essentially down, so it becomes 0. If it was 5 or greater, we'd make this 3, right? So it'd be 353 if this last number is 5 or greater. Then equal to 5, we'll also round up. Okay. All right. Problem solving strategy. So engineering is about following processes and following a methodology that will give us consistent results. That's also easy to communicate those results. So make sure you understand the problem, what it's really asking for. If you have any assumptions, you may need to do that. Maybe you're doing a force problem on the planet, on Earth, and it doesn't say, hey, this is on Earth. You can maybe assume it's Earth, so you assume gravitation acceleration is the Earth's gravitation acceleration, something like that. Okay. A lot of times, if things aren't given, then you'll have to make some assumptions. Okay, and then you just indicate whatever assumptions you made. Right. The next thing is, what are your major steps in solving the problem? And, a lot of times, you kind of work backwards. You kind of like, what am I looking for? And you can kind of look back and try to, by step, work backwards and figure out what is what your unknowns are and finally get to a point where you know those values or can calculate those values, then you work forward again and solve the problem. Okay. But that's really, this is the part, alternative creative solutions. This is where, you have to think it out and plan it out, how you're going to solve it. All right. So you should always spend some time doing this before you just jump in and start to calculate. Right. And yeah, alternative creative solutions, there's alternative solutions just about for everything, right? Some may not be good, but you don't really have a lot of time, probably going through alternative solutions. But sometimes you might want to do that to see if you come up with the same result. Okay. And the last one, carry out equations. Estimate your answers. You know, order of magnitude could be one back of napkin type of solution, which is really essentially order of magnitude for that. But sometimes you could just visually, our problems, we have diagrams typically. You can visually get an idea and saying, oh, is that a reasonable result, right? So in terms of your answer, is it reasonable for the problem, what they're asking for? Avoid simple calculation mistakes and then reflect on, right? And this part would be like, oh, is it a reasonable result? Does it make sense? Do you want to go and try another approach to figure out and see if that was, your solution was valid, to verify your solution. Okay. Here's just a simple problem, going through and doing conversion, right? Unit conversion. Just, list it out what your conversions are and then put them out and then just go through with the cancellation process. Then you can see that, oh yeah, my last units are meters per second, which is what you wanted. Okay. And what do you recognize like this? What's the value of this? It's just one, right? These are conversion factors. This is just one. So this doesn't change the magnitude of the answer. It's only changing the units. Okay. All right. Yeah, that's the same. Essentially the same thing here. Okay. So that's pretty much it for this one. So chapter 1 is, there's a little math and some concepts in there, but it's pretty, it's hopefully you've seen all these things and it's pretty much all review in the past. So like from physics or intro to engineering, you've seen it. But here's the main points. Okay, gravitation, then problem solving strategy. And that is it for this one, for chapter 1.